everybody, and welcome to the NPTEL online certification course on semiconductor devices for next generation FETs, and this is a physics perspective. This is lecture number 13 and the topic is capacitance modeling for high and low frequency, part 3. So, in our previous lecture we had looked into the variation of various parameters, especially the transconductance and drain current with respect to applied biases as well as with applied frequency of these biases. Now, let me come to a very important region within the semiconductor MOS device space, which is known as the moderate inversion. In most of the books or in most of the literature available to you, this moderate inversion is not dealt in a very big fashion, right. We generally say that you have a weak inversion and then you go to a strong inversion case. The region which is basically a moderate inversion is many a times left out in the discussion. So, the behavior of the various small signal parameters in the moderate inversion region is actually very different from a weak and a strong inversion region. I will explain to you why is it like. Let's go first of all in the weak inversion region. In the weak inversion region, the primary reason for the transport is basically diffusion, right. And in the strong inversion region, the primary reason is basically drift diffusion, right. So, you have more of drift because of relatively larger number of carriers and a larger number of electric lines of forces in the longitudinal direction. Whereas in moderate inversion, the number of charge carriers available at the silicon dioxide interface is not as small as weak inversion and is not as large as the strong inversion. So there is somewhere in the middle, and you will now see that there will be heavy non-linearity because of moderate inversion coming into picture. So, on the right hand side, if you look at the graph here, this graph, if you look carefully here, it basically gives you a normalized value of two parameters. The first parameter is GM by IDS and the second parameter is basically just GM, right. So, these are the two parameters which we are looking into, and this is normalized. So, if you see GM max, GM by GM max is get the value and GM by IDS gives you the value here. So, the maximum value of both these quantities will be obviously equals to 1, and as the inversion varies or as the region of inversion varies, the variations will take place for this quantity. So, if you look very carefully, then GM by IDS, which is this one, right. So, let me say this to be as a moderate inversion region. This is my weak inversion, this is my moderate inversion, this is weak inversion and this is strong inversion, right. So, if you look at the weak inversion, both the parameters GM by IDS and GM by GM max is almost constant. One is approximately equals to 1, another is approximately equals to 0. It implies that at weak inversion, GM by GM max is approximately equals to 0, which effectively means that your GM is equals to 0 or transconductance is equals to 0, and that is expected because when your transconductance is not exactly 0, but it is very close to 0. So, you see this figure is almost going towards 0, right, and that is the reason it is almost flat. So, even in the weak inversion, since you are not having any extra charge carriers available, your transconductance does not show a change, and that is the reason it is almost constant. Let us look at the other part, GM by IDS. So, the obvious logic is if GM is small, then why GM by IDS is large? The reason is large because IDS is very small. It is of the order much smaller order as compared to the standard ID max, and that is the reason GM by IDX is relatively a large quantity reaching maximum value somewhere at the edge of the weak inversion. Now, let us move one step forward. Now, in one step forward, if you go to the moderate inversion region, or let us come to the strong inversion, that is much more easier to handle. In the strong inversion region, this quantity which is GM by IDS upon GM by IDS max almost goes to 0. The reason being your IDS value is so large now because you are in saturation region that the quantity GM by IDX actually goes down. Now, if you look at GM by GM max, this goes almost to 1. You will ask me why this happens, because in the strong inversion you have largest number of carriers available in the inversion region and therefore the device is highly sensitive to variations in the gate voltage. So, if you give a small change in the gate voltage, you would expect to see a large change in the drain current, and that is the reason your GM value is typically large, almost saturating to a value equal to 1, whereas ID GM by ID max goes saturates to almost a 0 value. Somewhere in the middle you have this moderate inversion region coming into picture. In the moderate inversion, if you see, GM by GM max shows a rising trend, right, a rising trend, and GM by ID shows a falling trend, which, and this, the reason is very specific, that this is the region where your ID starts to increase and GM starts to also increase, but the rate of increase of ID is much larger as compared to that of GM, right, and that is the reason you see here. For very strong VG, there is a dip in the value of GM as well, right, and this is to do with more of reduction in the mobility. So, in the moderate inversion is the region, which is this one, is a region where you actually see a transition taking place, whereas in the weak and strong inversion it is almost constant. Now, the obvious reason is why therefore we want to study moderate inversion. The reason we want to do that is that if you are giving a signal on the gate side and it is varying very slowly, then a substantial amount of time will be spent by the device in the moderate inversion region, and therefore its characteristics should be known to the design engineer a priori, and that is the reason we generally study moderate inversion, right. Okay. So, as I told you, look at the last point of this slide, that it says that obviously if you are not able to predict the variation of the current and the transconductance near the moderate inversion region or near the threshold region, it gives you a wrong result, right, and therefore for all analog applications the moderate inversion region happens to be a very important critical aspects available to you. Let me come to now a new topic, that is the medium frequency. We are looking now at medium frequency small signal model only for the intrinsic part, right. Now, what is this concept of medium frequency? How do you actually define medium, low or high frequency? I will give an example. Let us suppose you have the number of charge carriers available. You are giving on the gate side a signal which is very high, of the order of few gigahertz, let us say multiple gigahertz, right. So, it effectively means that the charge carriers in the inversion layer should be able to respond to that frequency, right, because there is some transit time, right. You can understand when you give a positive and a negative say pulse, let us give a positive pulse and you give a negative pulse, the electrons are attracted towards the positive pulse and repelled from the negative pulse. Now, if this positive and negative pulse are varied with a very fast rate, the electron will not be able to sort of react to the changing electric flux, and therefore it will stay where it is, it will not react. Whereas, if the frequency is small or medium, right, there will be small amount of the electrons will be able to respond to the change in the value of the electric field. Now, look at the first point, that when a small signal voltage is applied to a MOS transistor, they are varying very fast, right, let us assume. Then the small signal terminal currents can vary very different from the low signal model. So, if I have a low signal model, right, let me come to the point. So, if I have let me come to a point that where the small signal currents can be very different from low frequency model. When you are actually applying a very large frequency signal, the currents will be quite different from that of a low frequency model, right. For medium frequency, we will be able to predict very easily the behavior if we consider these phenomena, charge storage effects, and you are assuming that there is a quasi static operation taking place here. What is a charge storage effect? I will explain to you what do I mean by that. Let us suppose I have a medium frequency signal been given to the gate side. Now, since the charges are not able to respond very clearly to the input signal, let us suppose, the charge will lag behind the signal and there might be some charge storage effect taking place, means charges will be stored at a particular point within the device, and this storage of the charge is known as the charge storage effect. We also assume it to be as a quasi static operation, right, and we will explain to you as we move ahead what is the meaning of quasi static operation in terms of small signal model. So, this is the basic idea of a medium frequency model. Let us come to the intrinsic capacitances in a medium frequency model. Uh, so how do we find out this capacitance or the intrinsic capacitances? Is that we apply a DC bias into the MOS device, assuming it to be as a 4 terminal device. So, if you look very carefully at this particular graph or this particular figure here, right, if you look at this figure here, there is a gate terminal which is here, metal gate. I have a drain terminal, I have a source terminal, and I have a bulk terminal. Please understand, these are all intrinsic capacitances. What do I mean to say? I have already discussed in our previous classes. I have an intrinsic cap. It primarily means that my LS and LD, that is the source and drain length, have been all assumed to be equals to 0, correct. So, they have actually gone to 0 and there is no source or drain length available to you as such. That gives you the intrinsic. This is the intrinsic. What you see in front of you is only the intrinsic part, which consists of gate, oxide and the substrate. In the substrate, I have applied a body bias, I have given a positive gate voltage here, I have given a positive source voltage here, I have given a positive gate voltage here, and I have given a positive drain voltage here. So, all are positive and all are fixed DC biases. So, when we write subscript 0, when we write QG0, it basically means I am giving a DC or a quiescent current available here. So, a DC is being given here, and that is the reason you see this to be as QG0, this you see as QD0, this you see as VS0, and this you see as VB0. So, there are 4 terminal, and we can assume the ground to be an arbitrary 5th terminal across which these are referred. So, this is again a ground based sort of intrinsic capacitances. With respect to ground, I am trying to find out the intrinsic capacitances for each of the terminal. Now, as you can see, if I apply a positive gate bias, I will have positive charges sitting on the metal side, and therefore, there will be negative charges on the channel side, right, and there will be fixed ionized negative charges available much below, right, because of the positive bulk potential which you have applied, and that will be basically the depletion region. Now, since you have applied a positive gate bias or drain bias, you see the depletion region thickness goes on increasing as you move towards the gate side. You see, it was initially this much and then it goes to this much. The inversion layer goes on thinning and the depletion layer goes on increasing as you move towards the drain side, because larger and larger drain bias will imply a larger reverse bias and therefore a larger depletion thickness. Now, let us come to the fact that, because we are not trying to derive the capacitance concept from these intrinsic layer. So, let us take up one important point and let us take one by one the case. So, what we will do now is we will fix up my drain bias and bulk bias, which is the constant value. However, what we do is we also fix up our gate bias, let us suppose, and then what we do on VSO, which is my source bias, I superimpose on that del Vs, del Vs, del Vs is the DC bias which is add on to the intrinsic value of Vs0. So, the total voltage which you will see here is Vs0 plus del Vs, that will be the amount of voltage which will be in gate side on the source side. Now, because of that, if you look very carefully, because of that, because you are putting a positive gate bias on the source side, there will be a decrease in the gate charge, right, there will be a decrease in the gate charge. And you can understand why there will be a decrease in the gate charge, because since you are applying a positive bias, you are effectively pulling all the electron away, and therefore, the mirror charges will actually reduce, and that is the reason you see that we define CGS, gate to source, right, if you look at this particular point, to be approximately equals to minus del QG and del Vs. So, if you change Vs by del amount, del Vs, the charge will change by del Q, and the value of charge will actually reduce with increasing value of del Vs, right. So, if you do a small increase of the source voltage, right, and we will see CGS happening here. Now, let's take up another experiment, that what we do is we now bias our source voltage and let us say bulk voltage constant, and we apply a drain bias here, more positive drain bias if you apply. Exactly same thing happens as a source, because it is a symmetric device. Why? because as you go on increasing the value of the drain bias, since the reverse bias increases, you will actually see a larger amount of bulk charge being created, which effectively means that your gate voltage, gate charge will reduce. And therefore, if you look at CGD, the CGD is referred to as minus of del QG del VD, which means that if you actually change the gate bias or drain bias by an amount del VD, then you will expect to see a change of del QG on the gate side, and it will be negative in nature, right. If you look carefully at the figure, first figure, this figure and this one, this and this, then you will see that in the first figure, on the source edge the depletion thickness is increasing. In the second figure, the drain edge, the depletion edge is increasing, right. So, in the first case, the depletion thickness is almost constant as you move from source towards the drain end, whereas in the second case it increases, right. Let us come to the last point, and we say that my drain is fixed, my source is fixed, right. Now I applied a bulk bias. So, if you apply a bulk bias del VB with a positive sign onto the bulk side, you are effectively increasing the electric field in this direction. Once you are effectively increasing the electric field, your gate charge again reduces. Why? Because you are pulling away the electrons from there, right. And therefore, what happens is my CGB, gate to bulk, if you find out, is del QG del VB, right. So, we have just learned CGS, which is this one. We have also learned CGD, gate to drain. We have learned bulk to source, right, and we have body to source and body to drain, and we have gate to bulk. So, there are 5 capacitances which can be easily thought of in this case, and we are assuming that in all the cases the device is in the deep saturation. Deep saturation means my drain to source voltage is always greater than equals to VGS minus VT. This I am assuming for all practical purposes, correct. So, you see, interestingly, I have not changed my gate bias, I have kept the gate bias constant, right. So, please keep in mind when you say CGS equals to del QG del Vs, this implies that my for the first case, it implies that my Vd is constant, right, my Vb is constant and my Vg is constant. Similarly, when you do del Vgs with respect to del Q versus D, then I assume that Vs is constant, Vb is constant and Vg is constant. So, with this assumptions, these are coming. Please understand that when you have multiple phenomena coming into picture, you have to apply a principle of superposition in this case. So, I have explained to you the basic intrinsic capacitances which is available in case of a MOS device working in the saturation region, right, and that gives me a good idea about how the saturation region works. Now, the same thing which we discussed just now, if you look very carefully, this is shown much more pictorially, that if you apply a value of del Vs, right, then you will have an effective charge minus CGS del Vs on the gate terminal, and you will therefore have a positive del CGS del Vs on the source terminal, on the source side of the terminal. So, if you look at the first part which is written here, you will see that is if you look at this expression, then del QC is the difference between the total steady state gate charge when the source voltage is fixed at Vs plus del Vs, and the steady state charge when the source voltage is held at Vs. So, when your source voltage was held at Vs, you have charged something, say A, and when the voltage was increased to Vs plus del Vs, it has become B. So, A minus B is basically del QC or del QG, whatever you want to name it, right. And therefore, I see that I have minus CGS del Vs on the top capacitor, and you will have plus CGS del Vs on the bottom capacitor, and we define CGS to be equals to minus del QG del Vs. I am assuming non-quasi static model. I am also assuming that Vg, Vd and Vb are all constants during the value when I am measuring the value of CGS. In reality, not true, then you have to take principle of superposition in order to explain the value of CGS, right. So, just to recapitulate and give you the small signal equivalent circuit diagram in medium frequency, these are the values which you say CBS, CBD, CGD and CGB, and therefore, if you look, this is an extension of the previous small signal model. We have GM VGS which acts as a current source. GM is basically your again del id, right, del VGS, and if you multiply that with VGS, I will get the current here. So this current is basically the drain current which is flowing through the device, and I have a GMB VBS on the bottom side, this one. This is the contribution from the back channel which you give, or the back gate which you give, right. And we also saw that I need this expression GM up by GMB to be as small as possible, right, and should be much smaller than 1. So basically GM should be much larger than GMB. Your back gate should be less prone to sensitization as compared to GM. Then you have CGS here, and then you have CGD, gate to source, gate to drain. I have CBD, bulk to drain, you see, bulk to drain. I have CBS, which is body to source here, and this GSD is basically my conductance, source to drain conductance, and that is equals to 1 by RSD, which is basically the resistance between the source and the drain, and that is GSD, right. Higher the value of GSD, more current will be possibly flowing through the channel. Higher the value of GM, more will be the current flowing through the channel, right. And therefore, I would expect to see that the small signal equivalent circuit diagram for the intrinsic part of the MOS device in medium frequency looks like the one which is shown here at the bottom of the presentation slide. Now, let us finalize this whole expression by a single diagram, and we assume that the oxide layer is typically small, and let me plot for you the value of capacitance. So, these are not normalized capacitances, but these are capacitances, the absolute value is mentioned here, and what we are doing is we are plotting capacitance which is in picofarads with respect to the various regions of operation, which is non-saturation and saturation, as you value VDS. So, we are not varying VGS here. I am basically trying to see how does small signal intrinsic capacitance vary if you go from non-saturated to saturated stage in strong inversion region, right, for a large gate device. So, channel lengths and widths are very long, and your oxide thicknesses are also very large. With that in mind, let us look at this figure and let us see how this works out. If you look at CGS, we have already seen it. If you look at CGS, do not look at the dotted curve, look at the straight curve which you see. Then you see that till non-saturated it shows a linear increase, and then it saturates after in saturation. So, most of the capacitance saturates in saturation region, and the reason is that saturation region is a region where you do not see a further increase in its corresponding gate charge. When the charge is not changing, obviously the capacitance will not change, right. So, and it becomes constant almost, or what we can say is that there is a linear increase in the charge with respect to the gate voltage. But since it is a drain voltage which we are talking about, let us see how one by one how it works out. So, when your drain voltage is relatively very small, and in the non-saturated case, your CGS shows almost a linear increase, right. Why? Because as you go on increasing the value of VDS, more and more charge is getting accumulated onto the source side and on the drain side, and as a result you will see a linear increase in the value of CGS, right, from 0.15 to approximately 0.20 for a standard device, and then it starts to saturate. Saturates why? Because your CGD is, if you look at CGS, it is basically del QG, right, with the negative sign del Q del Vs, right, del Vs for a fixed value of VDS. Now, once you enter saturation, this shows a constant term, because for the same increase in the value of VDS, you will go on increasing the same, you will expect to see a same increase in the value of the charge. Let us look at CGD, gate to drain. Gate to drain actually falls down reduces with respect to the value of VDS, and the reason is why does it sort of reduces, because as you make a drain voltage larger and larger for a fixed gate voltage, right, as you make your drain voltage larger and larger, what actually happens is that the effective charge reduces, and therefore your CGD starts to reduce. You see that this reduces to drastically low value and almost becomes 0 at saturation region, almost 0 it becomes in saturation region. Let us look at CBS and CBD. So, CBS and CBD do not vary too much with the drain voltage, and the white CBS, it is basically body to source, right. So if you, so it is between body to source, please understand, body to source, if you look very carefully, it is something like this, right. This is the drain voltage which I am giving, and this is my body here, body voltage, this is the body. So body to source is between these two. So if you vary this on this side, this does not get too much affected, and that is the reason you see your CBS is almost constant across non-saturated as well as in the saturated condition, right. CBD, let us look at CBD, it is basically body to drain. Body to drain also starts to fall down because more reverse bias is there. So more inversion charge reduces, and therefore your CBD starts to reduce, and it goes down here. At saturation goes to 0. So to take away from all this discussion is, in saturation the value of your CGB, right, CGB, CGD is almost equals to 0 or very low value, and CBS is almost independent. So let me write down for you, CBS is not a, to a larger extent not a function of VDS, though it is, but first principle it is not. CBD is again goes down with increasing VDS, right, and then CGD actually again goes down with increasing VDS, and the reason you understand why is it like that, both becoming 0 approximately equals to 0 at saturation. And CGS, what happens to CGS? CGS increases with VDS in non-saturated case and then becomes constant in saturation, right, and that gives you a good idea how the behavior will be. You will ask me why this is important. This is important because of the fact that when you want to calculate the capacitance values at various bias conditions when the MOS device is placed, this information will be quite critical, right, and you can actually extract it numerically as well as analytically, the values of CGS, CGD, CBD and CBS, right. With this we have let me finish this slide and let me recapitulate what we did in this part here. We looked into the basically the concept of small signal intrinsic capacitances, CGB, gate to drain, we can also write down gate to drain, and we can also write down bulk to source and CBG, right, bulk to gate. We say that then finally we looked into the concept of how will you calculate, how to calculate the value of these values, calculate these values, right. The third point was how these parameters are basically a function of VDS that we are trying to find out, right. So these three things we looked into this class. We will subsequently discuss other quantities in the next class. Thanks a lot.